we've been looking at motion in one dimension, in particular looking at the special condition of constant acceleration. I want to look at that further and look at some specific examples. In particular, what I'd like to talk about today are systems in free fall near the surface of the Earth. But to get there, I want to review a little bit of the structure of what we have with motion and constant acceleration. We started with our fundamental definitions, that the velocity is the derivative of position and the acceleration is a derivative of the velocity. Now, over here, I've sort of to remind us what that might mean in one dimension, where that one dimension is defined as the x-axis. And so you can see I sort of have a representation of this definition in words, as well as a mathematical representation of what that means. You can represent it mathematically in a number of different ways, but it's also useful to have an example of it so we remind ourselves of what that means. Okay, and from those fundamental definitions, we then derived functions that apply in under the constraints of one-dimensional motion with constant acceleration. So the acceleration is a constant. We found a function for the x component of the velocity as a function of time, as well as the x component of the position as a function of time. Now, these are all vectors, but we found in one dimension we can just work with the components where the sign, positive or negative, gives us information about the direction along the singular one-dimensional axis. And here we've identified the initial velocity is the velocity function evaluated at time is equal to 0. The initial position is the position function evaluated at time is equal to 0. Well, even that, as useful as that is, we can go even further to come up with other useful functions. I'll call this further useful functions. Because it turns out if I'm looking at a solved problem for motion with constant acceleration, most of the time I'm looking at for any two specific points in time. So I have these nice functions that are valid for all time, and that's great. But often I'm just looking for some sort of specific points in time, some t initial, some time initial, and some final time, for some initial time and some final time is what I want to say. Okay, for some initial time and final time, I'm going to have some initial position, which is the position function evaluated at the initial time, and some final position, which is the position function evaluated at some final time. There's going to be some initial velocity, which is the velocity function evaluated at some initial time, and then some final velocity, which is the velocity function evaluated at the final time. Now, also useful, I might be able to define is the displacement in one dimension is simply the final position minus the initial position, as well as the time interval delta t, which is equal to the final time minus the initial time. Okay, for these constraints, for these definitions, we now have a set of very useful expressions, relationships between all these parameters. We know that the final velocity is equal to the initial velocity plus the acceleration times the time interval. The final position is equal to the initial position plus the initial velocity times time plus 1/2 times the acceleration times the time interval squared. And these are the x components of the velocity as well. Okay. And then finally we have the final velocity squared is equal to the final initial velocity squared, and I'm keeping the x components just to remind myself, even though there isn't a velocity in the other direction, it's still the x component of the velocity, plus 2 times the acceleration times the displacement. And so these three equations give us two linearly independent equations. And that was important because in our problem solving, when we get into the algebra, we need as number of linearly independent equations as we have unknowns. And if you recall, we used these two to derive this third one, and so we have two linearly independent equations, but sometimes, depending on the situation, we have three to choose from. So it's important now to sort of look at how we got here. I mean, what is a student to do? I mean, do we have to memorize all these equations, and all these equations, and these equations? And remember, there's a lot more than these. These are just a single mathematical representation. We might be on the y-axis. We might have two different particles, particle A and particle B. Well, the answer is, these are our fundamental definitions, are probably the most important equations. On the other hand, if we're going to be spending a lot of time solving constant acceleration problems of single or double particles, it's going to be these relations that we use most often. And so experienced problem solver will be able to go back and forth. This becomes part of the mathematical toolbox that we use to solve problems, and then depending on the problem that we have, we want to choose the right tool. And so these are going to be incredibly useful, but they're still derived, and we should always remember where and how they're derived from our fundamental relations. Okay, so this now gives us something to go with, and we want to look at the specific condition now of freefall. Okay. And freefall is now something that's falling near the surface of the Earth. So we're going to constrain ourselves to near the surface of Earth. We're going to neglect air resistance, and we're going to maintain a work within our particle model. All right. Under these conditions, the acceleration is constant in magnitude and points to the center of the Earth. And so if I were to, well, let's just write that as a vector. So under these conditions, I'm going to have an acceleration, which it's a vector. It may be a function of time, but in this case, the magnitude is constant, and its direction is toward center of Earth. So I've written it this way on purpose. Acceleration is a vector, and this is the definition of the vector for freefall under these conditions. And so then it becomes a part of the problem we're going to solve, our coordinate system, our schematic, and everything else to then decide exactly how this applies to our specific example. So the first definition, sort of standard, is that we call the magnitude of this acceleration, this constant small g. So g is the magnitude of the free fall acceleration. Magnitudes, remember, are always positive. So g is a positive number. If we're in the direction is given toward the center of the Earth, and if we're in one dimension, there'll be a positive or a negative that determines the direction. But the magnitude itself, which we call g, is always positive. All right, so let's apply this to something in freefall. So we're going to stick with a simple enough problem. We're going to drop a ball from a height h and ask, how long does it take to hit the ground? All right, so for any problem, there's sort of a series of steps that I'm going to go through. The first step is to visualize the problem. Okay, so I'm going to drop a ball from a height h. I'm going to have my ground. Here's my ball, and it starts at some height h above the ground. Now, in general, there might have a specific height. It might be 10 meters. It might be 5 meters. Now, this is a particularly simple example, so I'm going to do the type of thing that physicists do, which is I'm going to represent this is a known height, but it could be any known height, and I'm going to call that height h, and so I'm just going to leave it in terms of h for this example. Okay, so now I have a coordinate system. Now I don't have a coordinate system. I have a picture. I need a schematic and a coordinate system. So a coordinate system, I need a 0 and a positive direction. So I could start my 0 axis where the ball's dropping. I'm going to, no particular reason, I'm going to call the origin of my coordinate system to be where the ground is. I'm going to call it my single axis x, and I'm going to have the positive x going up. That's as good as anything. If my algebra gets complicated, I can always go back and switch it around. All right, so this is the visualization step. I've got to have a picture, I've got a schematic, I have a coordinate system, 0 and a positive axis. And now I sort of move on to the brainstorming section. What sort of physics applies to the problem? What do I know? What do I want to find out? And so it's pretty straightforward. I know already that I'm going to use my constant acceleration expressions. In particular, this really lends itself to this idea where I have two specific points in time. Points in time. Looking at the context of my problem, I've got a point where the ball is released, a point where it hits the ground. This is, if I call it sort of asks to look at this initial time, this final time, and so that's what we're going to do. So my initial time is the time the ball is released, and I'm going to call that initial time 0. See, I have the choice to determine when the 0 of time is, and so I'm going to choose it to be my initial time. The final time is t sub f, and I don't know what that is. So what is the initial position? Do I know that? I do. It's h, and it's a positive number. It's in the positive direction from 0. The final position, well, what is the position at the final time? That's when it hits the ground. Immediately when it hits the ground, that's at x is equal to 0, so my final position is 0. My initial velocity, that's equal to 0 because I'm releasing it from rest, and my final velocity is then unknown. I don't know what that is. All right, and so I know that, so delta t, I know that, that's equal to t sub f because my initial time is 0. Okay, so if I go to look at these expressions, I can immediately see what sort of things do I know and not know. And if I look here, I know my final position, initial velocity, which is 0, and my acceleration. I should be able to find time from that expression. And I can. And so 0, my final position is equal to my initial position, plus my initial velocity times time, which is 0, plus 1/2 my acceleration, negative g times t sub f squared. And if I do the algebra, I have t sub f, the square root of 2h over g. And so here I've been able to find the final time. And you see I've done it even though I know what g and h are, I leave it in terms of g and h, and then I can plug in values at the end. That's the end of this example.